So now let's discuss the second case, or let's derive an integrated rate law for the second case when we have n equals 1. That is to say, first order kinetics. So just to remind you what we're doing, we're figuring out the rate of a situation where we have reactant A. So the governing reaction here is A going to products. So we're really interested in how the concentration of reactant A changes with time. So we're going to lose some of reactant A as time goes on. And the rate law for first order kinetics is the rate constant times the concentration of A raised to the power of n, which in this case is just 1. So now I'm going to collect all the terms that contain A on one side. So it's going to become dA over A. And the other terms I want to put on the other side. So that's going to become minus K times dt. So I'm rearranging it, and then I'm going to integrate it. Once again, if you haven't had integral calculus, don't worry about this part. You're going to be able to use the final derived equation just using simple algebra. So the integral of 1 over x is the natural log of x. So what we get here as we go from 0 to time t is the natural log of reactant A minus the natural log of reactant A at time 0. So this is going to be the natural log of A at time, the concentration at time t, and A sub 0 is the initial concentration. So that's the left side of the integral. And that is going to be equal to minus kt, taking the integral of the right side, the integral of minus k dt. So usually this is rearranged using the law of logarithms to say that the logarithm of the initial concentration of A over the concentration at time t is equal to kt. Okay, so that's just switching the signs and then taking the law of logs that the natural log of x minus the natural log of y is the natural log of x over y. So this is a useful form of the integrated rate law for first order kinetics. So you can use this to show how concentration depends on time when n equals to 1, when you have first order kinetics. Let's rearrange this. Let's actually take this version up here and rearrange it so it's in the form of y equals mx plus b so that we can plot it. I'm going to make my y in this case the natural log of reactant A at time t. And I'm going to just rearrange it so that I have minus kt plus the natural log of A sub 0. So all this is a rearrangement of that equation that I wrote up here. So you can see that. Now, you can see that it's in the form of y equals mx plus b, where y is the natural log of reactant A, and t and x is t, time. Okay, so this is y in my equation, and the t is equivalent to x in the y equals mx plus b form. So that equation, if I plot the natural log of A versus t, it's going to give me a straight line. So a first order reaction gives a plot of the natural log of A versus t with a straight line like this. The slope of the line is going to be equal to negative k. This is kind of similar to how it was with zeroth order kinetics. And the y-intercept, B, is going to be equal to the natural log of that initial concentration, as you can see from the equation just above. What else can we do? We can use this equation to derive an expression for the half-life for a first order reaction. So just to remind you of the definition of half-life, the half-life, which we denote with a t sub 1/2, is the time required to consume 1/2 of the reactant. In this case, we're talking about reactant A. So at the half-life, let me make that a colon, the concentration of reactant A is going to be half of what we started with, 1/2 of A0. So let's take that and plug into the integrated rate law. Okay, so let's take this and plug into the first order integrated rate law, which you may recall is is the natural log of A0 over A being equal to K times T 1/2, or K times T, which in this case would be T 1/2. So let's plug in the T 1/2 and all of that business. I am going to have the natural log of A0. And if I plug this relationship in, A becomes 1/2 A0 and T becomes T 1/2 if I plug into the integrated rate law. And let's rearrange this to solve for T 1/2. Notice I have A0 in the numerator and in the denominator, so I can cancel them. The 2 flips to the top, so I end up with the natural log of 2 being equal to K times T 1/2. The natural log of 2 is 0.693. So I can simplify this or just rearrange it to solve for T 1/2. And this tells me that the half-life for a first order reaction is going to be equal to 0.693, that's the natural log of 2, over K. So this is the expression that I need to use for the half-life for first order kinetics, first order chemical reactions. Let's do an example. Here's an example problem where I have the radioactive isotope 32 phosphorus decaying by first order kinetics. This radioactive isotope has a half-life of 14.3 days. So that means it's going to take 14.3 days for half of it to decay. How long does it take for 95% of a sample of it, of a sample of 32 phosphorus to decay? So I suggest you take a moment, pause the video, write down the problem, and think about how you would approach it before resuming. So because it says first order kinetics, that's telling us that we need to use the equation that we derived for the half-life for first order kinetics. So we need to take the fact that T 1/2 is equal to 0.693 divided by the rate constant. Now, we don't know what the rate constant is, but we do know what the half-life is because we were given it in the problem. So let's rearrange this equation to solve for K. K is going to be equal to 0.693 divided by the half-life, which is 14.3 days. So that's going to give me a K value in reciprocal days, 4.85 times 10 to the minus 2 reciprocal days, days to the minus 1. That's going to be my K value. So that's useful. But if I want to know how long it takes for 95% of a sample to decay, I'm going to need my equation for first order kinetics. So that equation is the natural log of A0 over A at time t being equal to K times T. Okay, that's just one of the forms. It doesn't really matter which form you use. I happen to like this form of it. This is just the form of the integrated rate law for first order kinetics. So now I have to figure out what to plug in. Let's look at the problem for a second. All I know is I don't know any concentrations, but I know that I want 95% of a sample to be gone. So whenever I'm dealing with percentages, I think it's useful to just assume I have 100 of whatever to start out with. So I'm going to say that my initial concentration, A0, is going to be 100. Let's say 100 molar because I want it to be a concentration. Therefore, the concentration at time t after 95% of it has decayed should be 5 molar. And again, I just assigned it 100 arbitrarily because it makes the math easy. If 95% of it decays, then I drop from 100 molar to 5 molar, say. You could have picked any number and then just taken 5% of it to get to the concentration of A at time t. So now I have concentrations that I can plug into the integrated rate law. So I get the natural log of 100 molar over 5 molar being equal to KT. I know my K is 4.85 times 10 to the minus 2 reciprocal days. And that is going to be my K, and I'm multiplying it by T. I'm interested in solving for T here. So this simplifies to the natural log of 20 is equal to 4.85 times 10 to the minus 2 reciprocal days times T. Solving for T, I should get an answer that T is equal to 62 days. Okay, so natural log of 20 divided by 4.85 times 10 to the minus 2 gives me a time of 62 days. So this tells me how long it will take for 95% of that phosphorus 32 isotope to decay using the expression for the half-life for first order reactions, and then also using the integrated rate law for first order kinetics.